All right, here we go. So today is the final review for statistics, or basically it's just exam 3, covering chapter 7, 8, and 9. So again, this is all on the online statistics course. And so moving in through here, so we got statistics. And when you go in here to the test review materials, it will be added down here. We are working on version B. So we're going to make the solution guide right now. We're recording the video right now. The blank review, it'll be out there as soon as we can. I've got the blank review right here that I'll put up on my screen and all that stuff, but the blank review will be there. Okay, so all this will be filled in today. Sorry that we didn't have the blank right away for you guys. But again, this is the final exam, or in other words, it's exam 3, test 3, chapter 7, 8, and 9. A total of 25 questions. I have my StatCrunch up and ready because during the exam, you should be able to access that. I also have my TI-84 right here ready for us. Should we want to talk about some computer stuff, or sorry, calculator stuff, not really computer stuff. Okay. So let's go ahead and get started. So again, as with every other review that we've done, I'm going to try and make sure that I tell you exactly where each question is coming from so you know what sections to look at. But for the most part, it really does go in order, starting in chapter 7 and working our way through chapter 9. Okay? So chapter 7, that's where this first statement is coming from. It is coming from the null hypothesis. Actually, that might be chapter 8. Let me double check. Because again, like I said, I want to make sure that I always tell you guys the right information. So actually, I think it's chapter 8. Because chapter 8 is where we started doing hypothesis testing. And I'm right. So this is actually coming from section 8.1 is where you'll find this information. So section 8.1. And this is just, basically it's a drop-down menu, okay? So the null hypothesis is always a statement about the blank, sample statistic or population parameter. And as we've always talked about, in chapter 8 and chapter 9, it's always about the population. Okay? So we are going to choose population parameter. So that's the answer to number 1. Knowing what the null hypothesis is always about. That's the H naught. Okay, number 2. This one is jumping back into 7.1. So it's kind of jumping around a little bit on you, but for the most part, I promise you, it's generally in order. All right, so number 2 says, in statistical inference, measurements are made on blank, sample or the population, and generalizations are made to a blank. Okay? So when we do measurements, that means we're actually collecting data and figuring information out. So when you actually collect data, that's all about the sample. So in this first one, measurements are made on a sample. And in the second blank, generalizations are always about the population. Because most of the time we don't know the population information. And so we generalize about it. Okay? So there's that piece. So number 3, this is actually getting a little bit into hypothesis testing. So this is actually coming from chapter 8, and the section would be on, make sure that I tell you the right section, where we practice writing hypotheses. And yeah, this is going to come from 8.1. 8.1, where you're actually going to write hypotheses. That's what this is about. So this is 8.1. So it says a research hospital tries a new antibiotic scrub before surgery to see whether it can lower the rate of infections of surgical sites. The old rate of infection is 2.9%. The null hypothesis is that the proportion of infections is 0.029. So right there, this piece right here where it says P equals 0.029, that's the null hypothesis. This is H naught. So they want us to report the alternative hypothesis to this. Okay. Now the key word in here is lower the rate. So our our alternative hypothesis has to be about lowering this number. So when we're down here, let's take a look. Population is less than that. That's definitely about lowering. But let's make sure that we check all this other information at the same time too. Of the next 1,000 surgeries, either more or less than 29 will result in an infection. We didn't talk anything about surgeries up here, so this is junk. The proportion of infections is greater than that our number, and we know that we want to be lower, so we know that's junk. The proportion of infections is not that number, so but again, we're all about lowering, so that's junk. And then these two, again, same kind of idea that we talked about in B, says of the next 1,000 surgery. Dude, we don't care about that, okay? Because we didn't talk about any kind of surgeries. So our gut in the beginning saying that it was A is correct. That the ha, and again, I'm writing out our answer key as we're doing this. So it might seem like I cut out for a second, but I'm really here. I'm just writing out what the answer is. Is less than 0.029. All right. So we chose A, and then the next part says we need to actually write out what the ha is. Okay. So part B. So the first piece is you're either going to do P or P hat. And again, it's all based off of your null hypothesis. So if the null hypothesis, whatever variable we use here, same variable we got to use down here. So we're going to go with P. And then in here, is it going to be not equal, less than, or greater than? And again, you already answered that question right here. Is less than. So make sure down here in this blank, you choose the less than symbol, the 0.029. So you're going to choose P less than 0.029. And there you go. And that's that guy. All right. So here we have some information. And this one is, again, it's coming from, I think we're getting this from, let me jump back here for a second. Let me look at the end problems. So looking up here. Yeah. So this one is coming from 8.1 as well. Wanted to say this might have been an 8.2 problem, but it's actually an 8.1. All right. So they want us to write the hypotheses and then report what the Z statistic is. Okay, so it says, according to a reputable magazine, the dropout rate for all college students with loans is 30%. Suppose that 102 out of 300 random college students with loans drop out. Complete parts A and B below. So the first thing says, give the null hypothesis and give the alternative hypothesis. Okay. So H naught is P. Remember that the H naught always uses equals. So in the first blank, you're going to choose the equal sign because the H naught is, H naught is always equal. Okay. And then over here, you put in the generalization, which is 30%, but you don't put in percentages over here. You actually write it as its decimal version. So you're going to put 0.30. Okay. Just like up here, they told us that the percentage was 2.9%, but down here, we don't use 2.9%. We used its decimal. So keep that in mind when you do this. Make sure that if you have a percentage, you put it in as the decimal. All right, so the ha. Right here is the key. It's saying that the dropout rate is not 30%. Okay? So that means it's not lower, it's not greater, it's just not this number. So down here, when we choose, we can't use equals. Equals is always reserved for H naught. So we're going to do the not equals. Whenever you say something is not that, you're really what you're saying is not equal. Okay? This is another way of saying is not equal to. So we're going to choose the not equal. And again, in the blank, you're going to put the 0.30. And also, I know that we want to choose the not equal because this is a two-tailed test. If you look right here, you got one, you got two tails. Okay. If there was only one tail on this, in other words, one blue area, we would have chosen either the less than or the greater than, depending on where the area was. So if it was just a tail down here, we would have chose less than. If it was a tail up here, we would have chose the greater than. But because I have both of these, that's a not equals. It's a two tail. All right, and then part B, they just want to make sure that you can read this. So what is the Z statistic? It's right here. And it says write an integer or decimal rounded to 4 decimal places. Well, it's right there for you. There is the Z statistic. You just got to copy that number down. So Z is equal to 1.5119. And there is number 4. Okay. All right, so number 5. So here is what I was talking about earlier. This is a one tail. This is a two tail. Okay. So number 5. Again, in this one, it says that, kind of just looking at over this, it wants us to choose which picture down below is the correct one, A or B. And then it's going to talk to us about the alternative hypothesis and basically the stuff that we just talked about. So this one is coming from I believe this is our section 8.2. Kind of looking at some things. Yeah, this is coming from 8.2. I mean, a lot of our sections kind of bleed together, especially chapter 8, because it's all hypothesis testing. So, but I want to make sure that you know where this information is coming from. So suppose researchers are testing people to see whether the rate of use of seatbelts has changed from a previous value of 86%. Suppose that in a random sample of 400 people, they see that 356 have the seatbelt fastened. Which of the following figures has the correct p-value for testing the hypothesis that the proportion who use seatbelts has changed? Explain your choice. Okay. So first thing is, what does it mean that it has changed? Because that's the key in this. Okay. So has changed is a lot like what we talked about right here. So it's another way of saying is not. Okay. Because up here, I could come in here and say, give the null and alternative hypothesis to test that the dropout rate has changed from 30%. See, there's that has changed. Okay. So has changed is another way of saying is not. So when we look at this, that means that this is a not equals. So whenever we have a not equals, I just talked about this, that means you're looking for a two-tailed. This is a one-tail, this is the two-tail. So part A, the answer is B. It is a two-tailed hypothesis test. Okay? It is a two-tailed. Now, part B. So it says graph blank is the correct figure. So again, you're just going to reiterate your answer here. So is it A or B? And you're going to put B. Graph B is the correct figure because the alternative hypothesis should be a blank, one tail or two tail. They also call it one-sided or two-sided. It's the same. So in that blank should go two-sided because it's a not equals. Okay. The test is to see if the proportion has blank changed for better or worse, improved. So again, what are we testing? The keyword is right up there for us. We want to know that it has changed. Okay. I have a feeling that I feel like these two should be together. Changed for the better or worse, improved. And I feel like there should be another one that says diminished or did not improve, something like that. Has not improved. So I feel like these should all go together, but that's all right. I mean, the main idea is changed. Yeah, I bet you these go together because it doesn't make sense if I just put has for better or worse. Yeah, but this should have said has changed for better or worse. But that's all right. We're good. We know that it should be the changed. Okay. So moving on to the next one, number 6. So number 6 says a researcher carried out a hypothesis using a two-tailed hypothesis. Okay, so again, we're still in chapter 8 here. Which of the following z-scores is associated with the smallest p-value? Okay, so which of the following z-scores is associated with the smallest p-value? So this question is coming from chapter 8.3, or I shouldn't say chapter, section 8.3. All right. So one of the things you have to remember is that the larger the z-score, the smaller the p-value. The larger the z-score, the smaller the p-value. Because the larger the z-score puts this out further away from the middle. So the larger the z-score, the less area that we're going to have to find, which that p kind of represents that area that is the shaded region here. So the larger that z-score becomes, the more it is further, the further it is away from the mean, the smaller your area is. Okay. So when we look at this guy for number 6, which one of these is the largest z-score? And by large, I mean you ignore the negative sign. Okay. So in other words, up here, when you look at all these, who is the largest number? It's actually A. We don't worry about the negative sign. Okay. it's like we ignore it. And so we've got 2.97, 2.63 or 36, 1.65, and 0.27. So which of these numbers is furthest away from the mean? This guy. So A is our largest z-score that will have the smallest p-value. Okay? And there we go on that. So part B says, explain. And that's just what we talked about. We need something that says the z-score has to be furthest away from the mean. Remember that the mean in the middle is always, this part right here represents a z-score of 0. So the furthest away we are from this line, which represents 0, the smaller our p-value. So we need something that says it. So here it says the closest to 0. That's not true. The furthest from 0, there we go. That's good. Has the smallest tail area, which I talked about, and thus the smallest p-value. So the answer has to be B. Because if you look at the next one, it says the furthest from 1. That's not true. Okay? We want to be the furthest away from 0. Okay? That's the important part. So the furthest away from 0. So that would be B. Okay, this one says close to 0, close to 0. That's not, we want to be far away from it. And this one says furthest away from 1. So I'm going to write down that answer real quick. So just bear with me. So it says the z score farthest from 0 has the smallest tail area and thus has the smallest p value. And there we go. Easy peasy lemon squeezy. All right, number 7. So number 7, again, this is all about null hypothesis and that information. So this was an example that they talked about in the book on how to minimize kind of dealing with that significant level and things like that. So this one is coming from section, tell you where to look. I'll even tell you the page where this example is coming from. And it's the balancing the two types of mistakes. And it's on page 374 in section 8.3. So in section 8.3. So it says, when a person stands trial for murder, the jury is instructed to assume the defendant is innocent. Is this claim of innocence an example of a null hypothesis or an example of an alternative hypothesis? So when the jury is instructed to assume the person is innocent, that is the null, because this is what you have to accept as true in the very beginning. Just like in the in a population, when we have a population parameter, we accept that as truth from the very beginning, and the alternative is what is trying to disprove, well, not really disprove, but make it so that the original null hypothesis fails. Okay, so it's got to be either B or C. And again, we accept it as truth. So B says then it is a null hypothesis since it is assumed to be false. Nope, we don't assume it is false. And then so C has to be the correct answer because it is the null hypothesis since we assume it to be true until evidence can prove otherwise. a null hypothesis since it is assumed to be true until evidence can prove otherwise. All right, number 8, moving right along. See, this is not a crazy exam, I promise you. If you know your stuff, you're going to be just fine. It's not crazy at all. So there is quite a lot to number 8. So there's a part B and a part A. So we're definitely running a hypothesis test in this thing, okay? So this one, I'm pretty sure is probably coming from 8.4. Let me double check, because I always like to make sure that you understand, again, where these are coming from so you can look them up if need be. So section, yep, 8.4, I was right. So part A. So let's read and find out what we got here. So this says a study reported the results of a randomized trial of whole body hypothermia cooling for neonatal hypoxia ischemic encephalopathy. Yeah, okay. So let's just go with the brain problems in babies due to lack of oxygen. Okay. So 26 of the 91 infants randomly assigned to hypothermia died, and 38 of the 97 infants in the controlled group died. Perfect. Complete parts A and B below. All right, so part A says, find and compare the sample percentages that died for these two groups. All right, so that just means we want to do a little bit of math here. So we know that we had one group that was in the hypothermia. And then we had a control group. Just going to write some information down. I'm going to jump over to our answer key page so we can talk some of this out. So control group. So in the hypothermia, it said we had 26 of 91. And in the control, we had 38 of 97. Okay. So jumping over to this guy. So in here, they want us to find the percentages. So in order to find the percentages, you take what happened over the total. Okay. So 26 is what happened, because 26 of them died in this group. Out of how many? 91. Over here, 38 died out of 97. So we want to find these percentages. So we just go to our calculator and we do a little bit of math. No worries. 26 divided by 91. And there it is. And then let's jump back. Percentages. Round to 2 decimal places as needed. Okay. So again, you've got a whole number here of 0.2857142857. So it's like a repeated. And then let's get the other one real quick. 38 divided by 97. So that gives us 0.39175257773. Okay. So let's jump back to this. So these are the decimals, but remember, we got to turn these into percentages first. So I got to move my decimal 2 places. You can't round yet. All right. You got to get your percentages first. So if I move my decimal 2 places to the right, I get 28.57142857. If I move my decimal 2 places to the right over here, I get 39.175257773. And now you can actually get the percentages and round to 2 decimal places. So it'll be 28.57%. And then over here, you'll get 39.18 because the 5 says, hey, 7, go up. So there are the 2 percentages. So if we go back, percentage of babies in the treatment group that died, 28.57. Percentages of babies in the control group that died, 39.18. So the last part here, the death rate was greater for the babies in blank. Well, which one was the higher percentage? And you'll select control. Okay. So that's part A. Now, part B, they want us to run a hypothesis test on this. Okay. Well, that's not too crazy, I promise. So in this one, when you are dealing with this, so it says the test hypothesis for the death rate is less for those treated with hyperthermia at a 0.1 significance level. Let P1 represent the proportion of babies with these problems that would die after receiving the treatment, and let P2 be the proportion of babies with these problems that would die without treatment. So this is the control, P2, and this is the experiment, P1. So when we write the hypothesis test for this, H naught is always equals. So there's only one choice here. You're going to choose the equal part. P1 equals P2. We assume they're the same. Okay? So P1 equals P2. The treatment group equals the same as the control group. For the HA, we want to show that the hypothesis test for the death rate is less for those treated. Okay? So that means that our P1 group is less than the P2 group. Okay? So when we're down here and we look, it's got to be this guy. Because this is the treatment group is less than the control group. Okay? So in this, when you're looking at these, when you're thinking about this guy, it's always important to make sure that you remember who P1 and P2 are. Because if P2 had been the treatment and P1 had been the control, we would have chose this guy. Because this would have been the control group and this would be the treatment group. Even though this is a greater than sign, it's all about who is who, okay? So just be careful on that. But in this one, thankfully, the words less up here match the symbol we wanted down here because this was the treatment, this was the control. And the control should be, or the treatment should be smaller than the control. Hopefully that makes sense as I was talking it out with you. So we're going to choose P1 less than P2. All right. So now we need to find the Z statistic. And I'm going to run this using StatCrunch. And then I'll show you the calculator. So first things first, StatCrunch. So we're going to go statistic. We're looking for Z statistics, okay, because this is all about proportions. And this is a 2 sample because we have an experiment and we have the control. And we're going to use it with summary, okay? So actually, we might want to use it with data. Let me double check that. I feel like it should have been with summary. Yeah, it's not data. It should have been with summary. So that means we need to figure a couple things out. 2 sample with summary. So we need the mean, the standard deviation, and the size. Okay. So the mean should be the same as the proportion for these. Okay. So let's make sure that we find everything correct here. Sorry about that. I had to just look something up real quick. I went into the wrong one. I said it was Z statistics, even though we kind of are dealing with Z statistics, but we're actually doing portion stats. So this is the one that we needed to go into. I'm sorry about that. As I say, because in here I was like, this doesn't make any sense. This is like way too much data it's asking for what we have. So that's not right. We're supposed to go into proportion stats. There we go. Now we're on the right track. And we go to summary. And here's everything we need. So remember that in StatCrunch, they put the P's all on the same side. So, I mean, this should always equal 0 right here. And then down here, you just put in the proper symbol, which is still the less than. That doesn't change. Okay. But we got to put in our successes and our failures. Or not our successes and failures, excuse me, the successes out of the total. And that's what we use to find the percentages. So in sample 1, which is the treatment group, we had 26 out of 91. In sample 2, we had 38, which is the control, out of 97. Now that we've got all that information in, and we've got the correct settings here, because it is less than, all we got to do is hit compute. And there we go. Here's our Z-stat. Here's our p-value. And that's what they want us to be able to write down. So when we go back to this, so it says, give me the Z statistic with 2 decimal places. So Z is equal to 2 decimal places would be negative 1.53. So there is our Z. And then I believe the next thing it asks for is give us our p-value, 3 decimal places. So we go back. Here is the p-value, so that will be 0.063. 0.063. Okay. So now we have all the information we need to answer the last piece, because we know the significant level, or in other words, alpha, is equal to 0.10. All right. Let's talk about if we did it on the calculator. In the calculator, you're going to go to stat, calculate, or sorry, tests, because you're doing tests. You've got a 2 sample proportion z-test. Okay, this is the guy we're working with because it's proportions. So you hit enter. We're going to put in our successes, which were 26 out of 91, and 38 out of 97. And down here, you want the less than. And then all you got to do is say calculate. And there's a whole lot more information. Okay, so here's here's actually the percentages that we were looking for in part A and part B. Or sorry, part A for our treatment group, control group. Here is the actual p-value when figuring these together. Okay, there's, or not p-value, but our mean of figuring these together. And then here is the p-value we found a moment ago. Here is that z-score we found a moment ago. So you actually get a bit more information in the TI-84 with this. Okay. So there's how you do it in the TI-84. You hit stat, go over to test, and you want the 2 proportion z-test. Okay. All right. So let's jump out of there. Let's jump back to this, and let's continue talking about this part. So now to answer the last questions, we got to analyze. So we want to know, is this less than or equal to 0.10, or is it greater than? Once we know the answer to this, we can figure out whether we reject or fail to reject. So this number is definitely less than or equal to this guy. And because we are less than the significant level, that means when we answer this question now, we, for the conclusion, we are going to reject the null hypothesis. Whenever you are less than or equal to the significance level, you reject the null hypothesis. Okay? So right here, it says the death rate for babies treated with hypothermia blank was different from, was greater than, was less than, was the same as. Well, we rejected the null hypothesis. So that means we're going to, that means we have significant evidence for the alternative. So we're going to say was less than. There we go. And that's how the cookie crumbles. Moving on to number 9. So number 9, again, talking about parameters and statistics. This, I think, is going to jump. This is where we jump back to 7 a little bit. I think we're going to do some, just to double check. Yep. Jumping back into number 7. So this is 7.1. So it says, explain the difference between a parameter and a statistic. Well, remember, parameters are about populations, statistics are about samples, so we need something to say that. So right here it says a parameter is a categorical measure of population, and the statistic is a numerical measure of population. No. Okay. A statistic is a measure of the population. A parameter is a measure of the sample. Close, but they're just backwards. So let's look at the bottom one, C. A parameter is a measure of the population. Yeah. And a statistic is a measure of a sample. Yes. There it is. It's C. Parameters are about population. Statistics are about samples. The reason why we don't like A, well, one, it's not a categorical measure. Okay. All the parameters that we deal with in here have to be numerical. Okay, the other thing is the statistic right here says it's a numerical measure of population. That's also wrong. So, answer is C. A parameter is a measure of the population. And a statistic is a measure of a sample. Again, I was just writing that down on our answer sheet. All right, moving on to number 10. Okay, again, coming from 7-1. Okay. So it says, explain the difference between a sample and a census. Every 10 years, the U.S. Census Bureau takes a census. What does that mean? So sample, again, it's like a piece of the population. Census, when it's talking about here, is all about the population. The U.S. is surveying everybody in the United States. Okay. So a census is more about talking about everyone in the United States. It selects everybody in the United States. Okay. So the difference between a sample and a census, the sample is over a small part of the population. The census is over everybody. Okay. So when we look at part A, or not part A, but piece A sample is a group of objects or people we wish to study. Okay. Kind of. This also says a census is a collection of people or objects taken from the population of interest. And that right there we know is not true. A census is not a collection of people taken from the population. A census is all about the population. Okay. Part B says a sample is a group of objects or people we wish to study. Okay. Again, kind of. A census is a numerical value that characterizes some aspect of a sample. And no, again, a census is not about a sample. It is about the population. All right. So C, a sample is a collection of people or objects taken from the population of interest. Yes, this is much better. Okay. Because it's a piece of the population. That's what a sample is. All right, so let's see what else it says. A census is a survey in which every member of the population is measured. Yes. When the U.S. Census Bureau takes a census, it conducts a survey of all people living. Yes, that's it. It's got to be C. Because if you look at the bottom one right here, a sample is a survey in which every member of the population is. That's not true. A sample is a small collection. So 10. The answer is C. And now I need to write out this long answer real quick. A sample is a collection of people or objects taken from the population of interest. A census is a survey in which every member of the population is measured when the U.S. Census Bureau takes a census. It conducts a survey of all people living in the U.S. Thank you for bearing with me on that for a moment. All right, number 11. Okay. Again, coming from 7.1. Okay. So lots of 7 1s here. Just want to double check, make sure, pretty sure. Yeah, okay. So it says the mean GPA of 4,000 students at a college is 2.33. The sample of 20 GPAs from the school has a mean of 2.56. Which is mu and which is X bar? All right. So remember that Greek letters are for populations. Variables, English letters like X and things like that, are for samples. Okay. So right up here, this says the mean GPA of all. That's the key word right there. So that means this is a population information right here. So the mean GPA of 4,000 students at a college is 2.33. That means 2.33 is mu. And then right here, keyword, sample. So that means this has to be the statistic. Okay. So this is the parameter. This is the statistic. This is mu, because mu is about a parameter. It's Greek. This is the X bar, because it's a sample, and English letters are samples. So down here we look. So the population mean is mu. The sample mean is X bar. There it is. It's A. Everybody else is junk. Although this is also true as well. Sorry, I thought there were possibly two answers on this, but this is actually I read it wrong. So it says the statistic is mu, and that's not right. Statistics are reserved for English letters, not Greek letters. So it is A. The population mean, or you could also call that parameter, is mu equal to 2.33, and the sample mean, or you could also call that a statistic, is X bar equal to 2.56. I almost thought there were two answers, but I read it wrong. Silly Mr. Armstrong. And that's okay. As long as we learn from our mistakes, that's the good stuff. All right. So this next one. This one is coming to us live and in living color from section 7.1 again. So make the two given tables into one table by combining men for capital punishment into one group, men opposing it into another, women for it into one group, and women opposing it into another. The student who collected the data could have made the results misleading by trying persuasion more often on one gender than another, but she did not do this. She used persuasion on 10 of 20 women and 15 of 30 men. So let's complete parts A through C. So the first thing they want us to do, take that information up there and make it into a table. All right, so for CP, as in capital punishment, against CP, as in capital punishment, I'm kind of making my own little table here. Men, women. Okay. So How many men are for capital punishment? All right. So here's capital punishment. That's 8 and 12. So there are 20 men for capital punishment. How many men are against capital punishment? And that's right here. 7 and 3. So that's 10. So in here, you're going to put 20 and 10. And then over here, how many women are for capital punishment? That's 2 and 7. So that's 9. Against capital punishment is 8 and 3. So that's 11. So down here, you will have 9 and 11. So 20 and 10, 9 and 11. Okay. So from here, we are going to find the percentage of men that support and the percentage of women that support. Well, that's a lot like what we did earlier. So we just got to continue that same kind of strategy here. Okay. All right. So part B, jumping into our sheet here. So there's that filled in chart that we just talked about. So part B, we want the percentage for capital punishment from men, and we want for capital punishment for women. All you're going to do is take what we want, which is 20, divided by the total. 20 plus 10 is 30. We're going to take what we want, 9, divided by the total. 9 plus 11 is 20. So we want their percentages. So we just go to our calculator and we do some little quick math. 20 divided by 30 equals, and let's go back here. Let's see what we wanted to round to. And it says round to 1 decimal place. Okay. So again, our full decimal is 0.6666666 repeating. And then the women is 9 divided by 20, 0.45. All right. So you got to turn this into the percentage first, which will be 66.66666 repeating. Turn this guy into the percentage would be 45 just 45. Let's just say that. And now they want you to round to 1 decimal place. Okay. So if we round this to 1 decimal place up here, this will be 66.7%. This is already rounded to 1 decimal place, but our computer likes us to put in the 0.0. So 45.0%. And there we go. So 66.7%, 45%. All right, so part C says, on the basis of these results, if you were on trial for murder and did not want to suffer capital punishment, would you want a jury of men or women? So based on this, who had the smaller percentage? The women. So I would want a jury of women. Would be preferable, as a blank percentage of them are not in favor of capital punishment. As a lower percentage of them are not in favor of capital punishment. And that's how we answer that one. Okay. Still moving on here. So number 13. Okay. This one is coming to us from 7.2, I think so. Let me double check. I'm making sure. 7.2, yes, 7.2. So, I mean, as you can kind of see, I think your exam kind of went backwards. It started with chapter 8, jumped to chapter 7, and then we're going to end with chapter 9. So it kind of flip-flops chapter 7 and chapter 8. Why? I don't know. All right. So part A. So it says a rifleman's gun sighting is adjusted incorrectly. He shoots bullets consistently close to 2 feet left of the bullseye's target. Sketch a graph of the target with the bullet holes. Does this show a lack of precision or bias? Then draw a second sketch of the target if the shots are both unbiased and precise. In other words, have little variation. The rifleman's aim is not perfect, so the sketches may show more than one bullet hole. All right, so part A, we need a target with bullet holes consistently close to 2 feet left of the bullseye. All right, so we want to be to the left. So that's not this guy and that's not this guy. So it's these two, okay? And it is consistent though. So B is the answer you're going to go with. B is the answer you're going to go with. Because these are a consistent group and it's to the left. This is not a consistent group, okay? So what does this show? And I'm kind of going to draw the bullseye on here. So there's 1, 2, 3, 4, 5, 6 circles. Three, 4, 5, and 6, and not in the center, not in the second one, but close to the third one. All right. So what does this show? Well, when we talk about accuracy or biased and precision, okay? So when we think about precision, you're thinking about the spread of the data, okay? The spread of the data. So being consistent means that there's very little spread. So that's why we chose this picture. And because there's very little spread, that means it does not lack precision, okay? So as long as you're close together, your precision is really good. This would be poor precision. And then bias is the accuracy, okay? How close are you to the truth? So this one shows that there is bias, okay? That there is bias here because we're not hitting the truth value. Our accuracy is off. So the answer to this second piece here, does this show a lack of precision or bias? It shows that there is bias because we are not hitting the center. All right. So draw a second target if the shots are both unbiased and precise. So that means no bias and we're good. So that would be C. When you're hitting the bullseye consistently, that's unbiased and precise. Because you're unbiased, that means you're very accurate. And precise means that all of your bullets are clumped together. Okay? So this has the example like here. This is accuracy because we're near the center, but poor precision. This guy right here, good precision, poor accuracy, or biased. This guy right here, again, good precision, but biased because it has poor accuracy. So part B is the answer C. Again, just going to draw me a picture for our notes. 2, 3, 4, 5, and 6. So here we're hitting the bullseye. All right, number 14, moving on. 14, according to a candy company package, a certain candy contains 22 orange candies. Suppose we examine 300 random candies. Complete parts A through C. All right, so in this one, talking about the candy company. This is coming to us from section 7.2. Okay. So it says, according to a candy company pack. All right, so we already read that. So part A, what value should we expect for our sample percentages? Okay, so if we know the population mean, then that's what we expect in our samples. Because remember that the population or all sample means should be hitting close to the population mean. So what should we expect? The percentage of the candies in the sample to be orange? 22%. So the 22 goes in that. That's what we should expect because that's what generally happens. Okay. What is the standard error? All right. So this is just a small little formula to find standard error. And let me tell you what that formula is. So flipping over to this, to find standard error, all we're going to do is we're going to take the square root of the population proportion times 1 minus the population proportion and divide that by the total number. Okay? So it's a nice quick formula. You already know the population proportion, P is equal to 0.22. Because again, we can't put in 22 here because it's a percentage. It's got to be the decimal. And you already know the total because we're looking at 300 candies. Just to make sure it was 300. Yes, 300 candies. Okay, so let's jump down into here. And basically when you plug in, it will look like this. 0.22 times 1 minus 0.22 all over 300. And all that is under a square root. And I can go straight to my calculator and let it do this. Second square root, alpha y equals, we're putting in our fraction, 0.22, parenthesis 1 minus 0.22, close, and down below 300. And you hit enter, and there it is. Okay, that's the same way I have it written on my paper. So we got 0.0239165,215. And it says to round to 3 decimal places. Okay. So 3 decimal places would be the standard error equaling 0.02. The 3 becomes a 4. There's our standard error. So now, when we come back to this, or let's see here, yeah, 3 decimal places. Now remember that this is also a percentage in disguise, this guy right here. So in disguise, it's really 2.4%. Okay. So remember that this is a percentage in disguise, this guy. But they actually just want the decimal. So part C. So it says to fill in the blanks. So we expect blank percentage of orange candies. We already answered that. So that's 22% to be orange candies. Give or take what percent? That's the standard error percent that we just talked about. And it says round to 1 decimal place. So if you rounded to 3 decimal places already from part B, when you turn this into the percentage, as I showed you here, it already is to 1 decimal place. So in that second blank, you're going to put 2.4%. So the first blank is 22%, second blank is the 2.4%. And there you go. There's number 14. All right. Number 15. Let's jump down to this guy. Okay. So it says a research poll showed that 1,216 out of 2,049 randomly polled people in a county favored the death penalty for this conviction of murder. All right. So it says, assume the conditions for CLT are met. Great. Makes life easier for us. Okay. Complete parts A and B. So in this one, we are coming from section 7.4. All right, so we've got this technology information right here. So it says, using the technology output given, write the following sentence. I am 95% confident that the population proportion favoring the death penalty is between blank and blank. So we need the confidence interval. So if you come up here and it says round to 3 decimal places, here is the confidence interval. Okay, so you just need to round these 2 pieces into 3 decimal places. All right. So the first blank will be 0.572. The second blank will be 0.615. Okay. And it just wants the decimals of these. If it wanted these to be the percentages, because this is actually a percentage, you would have seen the percent sign, and it would have said find is between blank percent and blank percent. Okay? So part B says, is it plausible to claim that a majority favor the death penalty? Explain. Okay? So remember, a majority means that you are above 50%. So if we look at this interval that we have right here, remember that those are percentages. So this guy is like 57.2%. This guy is like 61.5%. Okay? So is it plausible that a majority favor the death penalty? And the answer is yes, because all of this interval right there is above 50%. You have a majority in here. 57% is a majority. 61% is a majority. So we're looking for a yes answer. So that means C and D is out. So we're going to say, yes, it is plausible because the confidence interval contains values above 50%. Yes, it is plausible. It is a plausible claim because the confidence interval does not contain 50%. Well, even though this does not contain 50%, you still have majority in here. Okay? So the answer has to be A, because the confidence interval contains values all above 50%, which is a majority, as what we just talked about. So part B is A. Yes, it is a plausible claim because the confidence interval contains values above 50%. There we go. All right, moving on to number 16. All right, so it is now time that we jump into 9.1. So number 16 starts chapter 9. Again, we only got about 10 more questions. So again, this is a lot like what you learned back in 7.1, because 9.1 really kind of takes a combination of chapter 7 and chapter 8 and puts it all together, and dealing with sampling techniques of means. Okay. So 16 says a study of all the students at a small college showed a mean age of 20.3 and a standard deviation of 1.6. Complete parts A and B below. All right, so part A says, are these numbers statistics or parameters? Explain and choose the correct answer. All right, because we are talking about everybody, that's the population, which means it has to be a parameter because you are talking about everybody. So we need something that says that down below. So obviously it's not C and D because it says these are statistics. So it says the numbers are parameters because they are estimates. Nope, these aren't estimates. Okay. Part B says the numbers are parameters because they are for all students, not a sample. There it is. It's B. So the numbers are parameters because they are for all the students, not a sample, because you're talking about your entire population there at this small college. All right, part B. So it says label the numbers with the appropriate symbols. So again, since these are parameters, we are only going to use the Greek letters. So that means X bar and S are out because those are statistics. Remember, X bar represents mean, S represents standard deviation. And the Greek letters, remember, mu represents mean, and sigma here represents standard deviation. So when we're down here, the 20.3 was all about the mean. So that means in this blank, you're going to select mu. Mu equals 20.3. And in this blank down here, this is all about the standard deviation. See, standard deviation of 1.6 years. So in here, you're going to select sigma equals the 1.6. Okay. And there we go, number 17, moving on. So here, again, this is a 9.1 question, another one. So it says a survey of, so right here, survey of 100 random full-time students at a large university showed the mean number of semester units that students were enrolled in was 12.7. The standard deviation is 2.1 units. Complete parts A and B. So again, just like before, are these statistics or parameters? Because this is a survey and it's only 100 people at a large university. So if you think this is the full population, you're just silly, because there's no way you would classify a large university as having just 100 full-time students. Okay. Point Siena's campus alone for Valencia has over 100 full-time students. So obviously this is a sample. And since it is a sample, we are dealing with statistics. So it's either C or D. So C says the numbers are statistics because they are estimates and they are biased. Well, it's not biased, it's random. Okay, so let's read D real quick. The numbers are statistics because they are for a sample of students, not all students. There we go. The D's, the better one. It's all about statistics. I mean, granted, they are kind of estimates a little bit, but they're not biased. Okay, so the most helpful answer and correct answer is D. So the number or numbers are statistics because they are for a sample of students, not all students. There we go. Part B. So just like before, because these are statistics, we're going to use the English ones. So X bar and S are what we want. Mu and sigma gone. So remember, as I said a moment ago, that X bar represents mean, S is a standard deviation. So in here, the 12.7, that was the mean. So the first blank is X bar equals the 12.7. The second blank, the 2.1, that is the standard deviation right there. So you'll put S in the second blank. And voila, number 17, finito. Number 18, moving on. We're doing great. Yay. All right. So here it says the distribution of scores on a certain exam is normal. So this is the normal distribution. Okay. Way that we can write it. So N 30, 10. Okay. Which means that the exam scores are normally distributed with a mean of 30 and a standard deviation of 10. Okay. So this question is coming to you direct from, oh, that's a good question. Let's show you here, because I didn't tell you which section this was. If I remember right, I think this is still, yeah, this is still 9-1. Okay. Oops. So it says sketch the curve and label on the axis the position of the mean plus or minus 1 standard deviation, the mean plus or minus 2 standard deviations, and the mean plus or minus 3 standard deviations. So like what we've done before, they just want you to make the normal picture, okay? Remember that when you make the normal picture, that the mean goes in the middle, okay? So this is your mu, this is your standard deviation. So right here in the middle is mu. And I always put my numbers on top. That's just me. So right here is 30. And then how do I get to the first standard deviation? All I got to do is add or subtract 10 from it. So this gives me 40. This gives me 20. And then to get to the next guy, all I do is add 10, so that's 50. And then the next guy, that's 60. And then I continue the same way on the second side, -2 sigma and -3 sigma. So this will be 10 and that will be 0. So this is what our graph looks like. That's the one that we want, which in our case will be this one right here, B. Because if you look at this one, it put 40 in the middle, and that's not true. This one put 30 in the middle, but it's counting by 5s, okay? And that's not true. So it's this guy right there, B. All right, so that's part A. Part B says, find the probability that a randomly selected score will be less than 20. Okay, so shade the region below the normal curve whose area corresponds to this probability. So we want the probability to be less than 20. Okay, so that's what we're looking at. Well, all we need to do is just go into StatCrunch and run this information, and StatCrunch will also show us which picture it's going to look like too. Okay, but hopefully you already know which picture it should be looking at this, because it should look like C. Okay, because here, this is the only picture that's at 20 and less than. Okay, so the graph picture is definitely C. All right, so let's go ahead, and I'm just going to go ahead and draw that up real quick. Mine as well. Mu 1 sigma, negative 1 sigma. Sorry, this is taking a couple seconds. So 0, 10, 20, 30, 40, 50, 60. So the graph is C. We know that. Okay. We just got to find the percentage. That's easy enough. So we can go to our calculator. I'll do the calculator first. And you're looking at the distribution, and it's a normal CDF that you're running. And all you have to do is put in the information that you're dealing with. Okay, so we are less than, so we like the negative 1, E99. The highest we're going to go is 20. Our mu is 30. Our standard deviation is 10. And just hit paste. And there is our p-value. Okay, or the probability, I should say. So p is equal to 0.15, or actually, be better to write it up like this. Hold on, I'll show you how I wrote it up. Equals 0.156552596. But again, we got to turn this into a percentage because it wants the percentage. You can see that right here. See, percentage. So if we convert this to a percentage, we get 15.86552596. Let's see what it wants us to round to. It says write an integer or a decimal. Okay, I get what it's doing. So granted, we got a decimal here, so it doesn't want any rounding. So give me just a second, and I'm going to show you our piece here. P less than 20. So this is how I wrote it up. You're looking for the probability that P is less than 20. And this is what the calculator gave us. But if we think about what's going on, remember that this right here represents one standard deviation. And remember, we have that empirical rule that we know about. Okay. Remember, the empirical rule says that between here and here, that's 68%. Between two standard deviations is 95%. And between three standard deviations, it's 99.7%. Okay. So we can actually figure out this as an accurate percentage, thinking about what we already know. Okay. So if you remember that right here, this is half of my information right there. And remember that these two from here to here make up 34%, or actually 68%, and half of that is 34. So we're missing this piece that's not shaded right here is approximately 50 plus 34. 50 plus 34. If you subtract that from 100, you get the rest of the shaded area. So, and that makes sense because if I round this to the nearest whole number, I get 16%. But they want it to be accurate, just so you know. So let me run through how we did that again. Everybody from 30 and above is 50%. Between 20 and 30 is 34%. Because from 20 to 40, that's 68%. Half of 68, 34. So if I add those up from 20 and above is 84%. All we have to do is subtract from 100% and ignore the sign. It's not really negative. And that gives us a 16% because under this curve should be 100%. So that's where all that information came from. Okay. If we did this on StatCrunch, just so you know, again, StatCrunch will kick out the decimal, it won't be the 16%. But if we go to StatCrunch, oops, wrong one. So we can just get rid of that stuff. Go to graph, and you are doing, actually it's not graph, it's under stat. Go to, actually maybe it was graph. I'm looking for normal. Normal, where are you at? I know you were on here somewhere. Calculators, that's where it was. Go to stat, calculators, and go to normal. All you got to do, you put in your mean, which was 30, 10, not 110. We are, less than. Put in your 20, compute. There's the picture, and there's that same decimal, okay? All right, so there you go. StatCrunch and the calculator. Okay, moving on. Woo! So we are on, I think, 20 now, right? 20, maybe? Nope, 19. Just kidding. And you're going to do it again. So much fun. So much. All right, so this time it says round to the nearest whole number. So this is, we won't have to do anything kind of weird on this one. So again, we know that we are normal. We are 60, 5. So that 60 is mu, the 5 is the standard deviation. So they want us to sketch the curve. Okay. So again, this is coming from, whoa, what was this? 9.1 again? Yeah, 9.1. 9.1. So we're going to draw that graph. I drew it a little bit better. So in the middle is mu. Then I've got 1 sigma, 2 sigma, 3 sigma, negative 1 sigma, negative 2 sigma, and negative 3 sigma. Okay, so in the middle goes the mean, 60. And then we just add 5s all the way up and subtract 5s all the way down. So this is 65, 70, 75. This is 55, 50, 45. So that's what our graph looks like. And that will be, certainly not B because it's got decimals. Looks like it's A. No, it's not A. So we went up, they put 50 in the middle here. Kind of threw me off because I saw the 5s. It's not A, it's actually C. C, senor. So there's our graph. C. And then we're going to do the same thing again. This says find the probability that the randomly selected score is between 55 and 65. Okay. So between 55 and 65. 55, and 65. So when we're thinking about this, we're looking for the probability that looks like this. Okay? And the cool thing is, I mean, if you actually look at this, our graph, let's get that real quick. So you can actually see it. Sorry about that. Mu, 1 sigma, 2 sigma, 3 sigma, -1 sigma, 2 sigma, and 3 sigma. So 60, 55, 65, 70, 75, 45. So it says we are between 55 and 65. So the shading actually occurs in here, right in there. So if we actually come up here and look at this, we know that our graph should be A. Okay. Notice I didn't put any numbers on this, but it actually is A. And the cool thing about this is, I mean, we can use the calculator, but we really don't need to if we don't want to. You are between one standard deviation on this. And we just talked about that a moment ago. How much of my percentage is in here? That's 68%. Okay. But if we use our calculators again, just to kind of show you, you go to second vars, normal CDF. Again, we're between, so we're going to put 55 as my lower, 65 as the upper. And you'll have 60 and 5. Paste it. Look at that. There's a decimal. And actually, what does this say? It says round to the nearest whole number. So there we go. And I mean, if you round this to the nearest whole number, you'll get 68. Yeah, 68, which is what we said. Because again, that decimal is 0.6826894809, which as a percentage is 68.26894809%. Show you what I wrote down on my piece of paper. So there was the decimal, and then here's when we convert it to the percentage and to the nearest whole number. The 2 says, hey, 8, stay the way you are. So 68%. If you did it stat crunch, so stat crunch, we can actually bring up what we just had a moment ago, the normal calculator. And this time we're going to hit between. And you'll put in the 60, the 5. This one is now 55. This one is now 65. And there it is. Same decimal that we had a second ago. Okie dokie. So jumping out of that. Moving on. You guys are doing great. All right. So this one right here, number 20. This one in chapter 9 is from section. We're checking CLT. So I believe this is going to be in section 9.3. Nope. We are in section 9.2, almost section 9.3. So 9.2 on this. Yeah. All right. So it says the mean age of all 2,534 students at a small college is 22.3 years with a standard deviation of 3.3 years. And a distribution is right skewed. A random sample of 4 students' ages is obtained, and the mean is 22.8 2.8 with a standard deviation of 2.7 years. All right, so the first things first, I want to know who's the mu, who's the sigma, who is the standard deviation, who is the x bar. All right, so that's part A. So mu equals, sigma equals, standard deviation equals, x bar equals. So remember, Greek letters are all about the population. So right here it says the word all. So everything in this sentence is population. So it says the mean age is 22.3. So mu is 22.3 with a standard deviation of 3.3 years. So this is the sigma, 3.3. Right over here, it says a random sample. So sample, these are the statistics. The mean is 22.8, so that is X bar. And a standard deviation of 2.7, so that is S. So mu is 22.3, sigma is 3.3, standard deviation over here for the sample is 2.7, and X bar for the mean of the sample is 22.8. All right. So part B says, is mu a parameter or a statistic? So because it is Greek, that means it is a parameter. Because it is found from the blank. Parameters are all about the population. Kind of think about it like this. Parameter P, population P. Statistic S, sample S. The beginning letters match. All right. Part C, we want to check CLT. Okay? And in 9.2, when you learn the CLT for dealing with means, okay, you know that you had to check the following 3 pieces of information. So there were 3, all right? And those 3 pieces of information, jump over to my piece of paper, CLT, central limit theorem. Okay, so those 3 pieces of information were, 1, that you have a random sample and independent observations. 2, you have a large sample. And there was 2 ways to check this. You are either normal from the beginning and you're good to go, or if you are not normal, then your sample size had to be at least 25. Okay? Had to be at least 25. Okay. So from here, the third one is that you have a large population, or in other words, a big population. Okay? So in other words, the population size is at least 10 times the sample size. Actually, this should have been the other way. Sorry. So the population size is at least 10 times the sample size. So those are the 3 things we have to check. All right. So let's go back and let's take a look at this information. So our sample, it's random. That's good. And the observations are independent. So we're looking at student ages. Obviously, one student age does not affect another's. So observations are independent. So CLT, random sample, and independent observations are met. Okay. The next one, large sample. Well, if we look at this, our original distribution is right skewed. So it's not normal. So that means we got to rely on the second piece. Okay. Our data is right skewed, and our sample size is 4. So because we're right skewed, we can't work on that one. So we got to rely on this. Is our sample at least 25? And the answer is no. So right here, because of this, we are not met. So that means CLT is not passed. We are done with this problem. Okay? Because we failed to meet number 2. So when we come back to here, conditions met, and the answer is no. And it's not because of a big population, because the random sample and independent, nope, it's not that one, because the large sample condition is not, there it is. So the answer to part C is C. No. Because the large sample condition is not satisfied. And then there's a follow-up piece to this that says, well, what does the data look like? Well, the data will look like its parent. Okay, so what would the shape of the approximate sampling distribution of means look like? It will look like just what the population does, which means it's going to be right skewed. The means follow the population. Okay, so there's number 20. Yeah. Number 21. So this one right here says a random sample of 20 colleges was taken. Okay. The mean rate of graduation within 4 years was 42.6% with a margin of error of 5%. The distribution graduate rates is normal, complete parts A and B below. So here they want us to find that confidence interval based off of the means. So we found confidence intervals in 9.4, I believe. Nope, 9.5. Or sorry, not 9.5, 9.3. Gosh. So 9.3 is where we found the confidence intervals. All right. So in this one, they give us all the information we need. Okay. We know it's a random sample of 20 colleges. We know the mean rate. So we know our sample size is 20. We know the graduation rate or the mean, okay, is 42.6%. Okay, and we know that the margin of error is equal to 5.0%. So if we want to find the confidence interval, okay, all we basically got to do is take this mean right here of 42.6%, and we're going to add and subtract the margin of error. Really, really easy. Take the mean, take that margin of error, and add or subtract it. Okay? All right. So if we go to our handy dandy calculator, and I'm not going to bring up my calculator for this. You know how to bring up your calculator and things like that. So all we got to do is take 42.6 plus 5.0. And you get 47.6%. So that's the upper. And then we take 42.6 minus 5.0. And we get 37.6%, and that's the lower. So when we fill in the blanks in this, the first blank should be 37.6. The second blank should be the 47.6. Now we just got to make sure that we know which one. So again, this is all about confidence, okay, not probability. So we know that it is not B, okay? Confidence interval is not about probability, okay? It's how confident we are in our process. So, and this is all about finding the population mean. So our choice here that we want to go with is A. Our choice that we're going to go with is A, because we are 95% confident that the population mean is between these two percentages. Okay? It's not a probability, and it's not about the sample mean. Okay? It's about the population. So we're going to choose A. And our writing the sentence, we are 95% confident that the population mean is between, our lowest value was 37.6%, and our highest value was 47.6%. And there you go. Part B. So just doing a little bit of interpreting. Can we reject a population mean percentage of 22.4? So the question is, does 22.4 fall within that range that we had up here? Okay. So again, that was 22.4%. We jump back to this. So the question is 22.4% in my confidence interval of 37.6% to 47.6%? That's what they're asking. So if we look at this, no, this is not in there. So it is not in there. Okay, so that's important. It is not in my confidence interval. I want to stress that word not and make it all capitals. So what that means in terms of our problem, so that means we are going to reject. Okay, so we need an answer that says reject. So it's what, either B or D. So let's take a look. So it says, yes, reject the 22.4. Since 22.4 isn't in it, well, that's not true. So we know it's not B then, so it must be D. Okay? So this one is D because it says, yes, reject 22.4%, since 22.4% is not in the interval. It is not plausible. The population graduation rate is 22.4%. Yay. All right. Let's jump into number 22. So we're going to answer parts A and B down below. All right. So number 22 says that we're looking for confidence interval. So again, this is 9.3. All right. So it says a statistics instructor randomly selected 4 bags of oranges. Each bag is labeled 10 pounds and weighed the bags. They weighed 10.2, 10.6, 10.6, and 10.8. Assume the distribution is normal, so that's great. Okay. Find a 95% confidence interval for the mean weight of all bags of oranges. Use technology to help you with your calculations. So we're going to do that here in a second. So again, it's kind of like what we just did back in number 21. We're going to select a statement with our confidence interval in it. Okay. So we don't have to check the CLT because it's going to be met for this because they actually do want us to find the confidence interval. You know, you don't really have to worry about D happening in this one because, you know, again, if we check that CLT that we just talked about a couple minutes ago, it is random. One bag does not affect the other. So the first part is met. It's normal. So we don't have to worry about whether we had a large enough sample size because it's normal. And then the population is definitely large. Okay. There are definitely more bags of oranges than just the 4 that's given to us. Okay, so we definitely have a large population. So, and again, remember, if you take 4 times 10, that's 40. So in the universe, are there more than 40 bags of oranges? Yes. Okay. All right. So we got all that interval. CLT stuff is met. All right, so we just need to run our calculator information. So if we go to our calculator, if you're going to use the graphing calculator, the first thing is you're going to have to put your information in. So you're going to go to Stat and click on Edit, and you're going to put in the 10.2 and the 10.6 and another 10.6 and a 10.8. Okay. And just so you know, in 9.3, we are dealing with T statistics because these are all about means. So now we're going to go up into Stat and we're going to scroll over to Tests. And you are doing a T interval. A T interval. So number 8. So you're going to do it from data. And then down here, we got to change this to be L1 because mine says L3. So hopefully yours already says L1. If it doesn't, here's how you change it. You're going to hit second and number 1 because right there in blue it says L1 because that's where my data is. Don't change anything else. We want 95%. So hopefully this screen is already good to go, and you just scroll down to calculate and you hit enter. And there's our confidence interval. Okay. So we just got to select the correct interpretation. If we did it in StatCrunch, this is what you would do. So I'm just going to call this oranges. And we had 10.2, 10.6, 10.6, 10.8. Go to stat. We're doing t-statistics, one sample with data. Stats, t-statistic, one sample with data. So select oranges. We're not hypothesis testing, we're confidence interval. And now you're ready. Compute. And there's that same information again. Okay? All right, so jumping back into this. So we know our confidence interval now. So again, it's all about the population, and it's not probability. It's how confident we are. So again, chance is another word for probability. We already know the requirements were met. So C and D are out. It's between A and B. And again, it's going to be A because it's about the population. So A is our choice. And we are, and up here it says round to the nearest thousandth. So that's 3 decimal places. So we are 95% confident the population mean is between thousandth, 3 decimal places. So I'm going to, let's see what the calculator gave us 2, so not a good one to use. So we definitely need the StatCrunch on this. So 3 decimal places will be our lowest, 10.14, actually 150. So our calculator was actually A-okay. They just didn't show us the extra 0. So 150 and 10.950. So there we go. Which matches, again, our calculator, 10.150, 10.950. Okay, our calculator actually did the rounding for us. But again, I would always err on the safe side. You know, I like StatCrunch a lot. It's free. It comes with our stuff. Why not use it? Okay. So there we go. This is our answer right here. We are 95% confident that the population is between 10.150 and 10.950. All right. So 22 part B. We know what our confidence interval is. It says, does the interval capture 10 pounds? So are we going to reject or not? Okay. So again, we know our interval. In other words, what it's asking is 10 pounds in the confidence interval of 10.150, comma 10.950. And the answer to that is no. It is not. Okay? So it is not in the interval. So for us, that means when we come back here, we want something that says it does not capture it. So it's either B or D. And because it does not capture it, that means we reject. So B says do not reject, but D says reject it. All right, so we're going to choose D. And we're going to say no, it does not capture 10. reject the claim of 10 pounds because 10 is not in the interval. And there we go. Number 22 or 23. We almost got this. All right, number 23 is coming from 9.4. We are hypothesis testing. Okay, really these last three questions are 9.4 and 9.5. So 24 is 9.4, and then 25 is when we actually get to a 2 sample testing. So that would be 9.5. So 24, 23 is 9.4, 25 is 9.5. All right. So let's get to this. Let's do this. Let's wrap this up. So they actually did a lot of the work for us, which is great. So we just got to start reading through and answering some questions. Okay. So it says the health agency suggested that a local total cholesterol measurement should be 200 milligrams per deciliter or less. Records from 50 randomly and independently selected people from a study conducted by the agency showed the results and technology output given below. So here's our technology. Okay. And right here, you can see that information right there of our hypothesis testing. Okay. So it says test the hypothesis that the mean cholesterol is more than 200 using a significance level of 0.05. Okay, assume conditions are met. So CLT, we don't have to worry about. All right, so the first thing is determine the null hypothesis and the alternative. So again, we want to be, right here is all that information. Here's the null, here's the alternative. We just got to make sure we select the correct one, okay? So first off, we need an equal sign for the null. So A works, B works, F works. C, D, and E are out. All right, so we want to be more than. So that's not equal, so it's not that. That's less than. Here it is, it's F. So the first piece for our hypotheses, the answer is F, because the null is mu equal to 200. The ha is mu has to be greater than 200. Okay, so the next one says the test statistic is blank. Round in integer or actually don't round. Just write down what the test statistic is. So up here, that's the T. Okay, so in that blank right there, we have 1.49. And then again, do not round, give us the p-value. So that's the 0.071. Okay, so 1.49, 0.071. And then now we're going to interpret. So again, when we look at this, our alpha is equal to 0.05. So the question is 0.071 less than or equal to 0.05, or is it greater than? So this time, it's greater than. So what this means is that we fail to reject. Okay? We fail to reject or fail to accept. So when we come up here, it says since the p-value is blank, well, in that blank, we know that it is greater than the significance level. That means we are going to fail to reject. So we do not reject. Do not reject the null hypothesis. And there is insufficient, because when you do not reject, that means you have insufficient evidence. evidence to conclude that the mean cholesterol is more than. Okay? So there's number 23. Greater than, do not reject, insufficient. Okay, number 24. Again, I already told you this is 9.4. So it says in country A, the population mean height for 3-year-old boys is 37 inches. Suppose a random sample of 15 3-year-old boys in country B showed a sample mean of 36.7 inches with a standard deviation of 4 inches. The boys were independently sampled. Assume they have a normal distribution. Complete the rest of the information. So again, we're going to assume that all conditions are met. I mean, the good thing is that it's normal. Okay, obviously populations are much bigger than 15 times 4, which is, well, let's see here, 15 times 4 is 60. So hopefully there in a country there is more than just 63-year-old boys. You know, America alone has more than that. And it's definitely random, and 1 3-year-old boy's height does not affect another one. So again, you can see that all conditions are met. So the first thing we want to do is we want to determine the hypothesis. Okay, so the first thing is everything has to be in comparison with the population. So right here it says the population mean is 37 inches. That's the null. So we need something that says mu equals 37. So we can go with A, B, or F. Again, these are out because we don't have equals in the first part. So we know that the null, or H naught, mu equals 37. So down here it says determine whether the population for country B boys is significantly different from country A. So because we want to know if they're significantly different, that means not equal to 37. Okay? So basically we're saying is not the same. So our ha is that mu is not 37, or in other words, not equals, which means that we want to choose A as our choice. Okay? So A is our choice for that because we do not want to be equal to 37. All right. So now we need to go to our calculator or StatCrunch to run this information. All right. So if we go to our calculator, this time you're going to go into stat. You're going to go over to tests. And this time you're doing a T test. Okay. So we're going to put in our statistics. We're not going off of data. We're going off of statistics. All right. So when we do that, we know that our mu, that's our population. So that's 37. We know our sample mean. Go back to this. So I should probably write these down. Mu is equal to 37. Our sample mean, they told us up above, is 36.7. Our standard deviation for that sample, or S, is equal to 4. We just got to fill that information in now. Okay? So this one should have been 36.7. Our sample standard deviation is 4. And our sample size, I didn't write that down. Our sample size, we looked at a total of 15. So fill in that part in. And then now, because it is hypothesis testing, we are doing the not equal. So make sure that that one is highlighted. Okay? All right. So then all we got to do is come down to calculate. And we got all of our information we need. Here's the T. Here's the P. Okay? Coming back up to this, If we come back over here to StatCrunch, here's how we would run this in StatCrunch. So stat, we're running t-stats, one sample with summary. So again, the sample mean is 36.7. The standard deviation is 4. The sample size, 15. And we are 37 here and not equals. Compute. So again, there's all that same information. Okay? So let's fill in what we know. So our t is equal to, it says round to 2 decimal places. Okay, easy enough. And our p-value says round to 3 decimal places. All right. So t equals p equals. T equals, okay. Sorry, I was just looking at something. Our t equals, I like to use StatCrunch, negative 0.29, because we're doing 2 decimal places, right? Almost forgot. 2 decimals. Yep. So negative 0.29. Both of them have the same information. So there's t. Our p-value, 3 decimal places, which would be 0.776. I want to check my StatCrunch. 0.776. Yep, 0.776. Okay. And our alpha, they told us from the very beginning, is a significance level of 0.05. So alpha is 0.05. So again, we have to ask ourselves our question, is 0.776 less than or equal to or greater than 0.05? And obviously it's greater than. So that means we fail to reject. So as we look at this part, we're going to not reject. So it's either B or D. Okay. So let's look at these first. So we do not reject. There is no reason to believe that 37 inches is not the population mean at a significance level. Okay. We do not reject. The population mean is definitely 37 inches on the basis of these data at a significant level of, so we can't necessarily say it's definitely, but it has given us no reason to not believe it. Oh, wait a minute. Is definitely not 30. Oh, sorry. I was looking at the wrong one. There is no reason to believe that it's not. Okay. The population mean. So I'm going to go with B on this because you can't say it's definitely this. There's just no reason to not believe it is not. There was insufficient evidence to prove otherwise. Okay. So do not reject H naught. There is no reason to believe that 37 inches is not the population mean at a significance level of 0.05. So there's part A. Part B. So it says, now suppose the sample was 30 instead of 15. Repeat the test. So that's easy. I'm just going to go back to StatCrunch. You know, if you did this in the calculator, all you're going to do is replace the n with 30. So this time n is 30. Okay. The hypotheses all stay the same. The only thing we're changing is the n. All right. So all of our statistics still stay the same as well. Okay. So if I go to StatCrunch, all I want to do is go into the options and I want to edit. And I just want to change this to 30. Okay? And compute. So here's what we know this time. So our t statistic is equal to negative 0.41, because I believe it's going to make us round to the same thing too. Yeah, 2 decimal places, 3 decimal places. Okay? So 2 decimal places, 3 decimal places. So we go back. So negative 0.41, 0.41. Our p-value is 0.6842. Our alpha is still the same. So again, we're asking is 0.6842 less than or equal to or greater than 0.05. Again, it's still greater than. So we're going to fail to reject. Okay. So 24, part B. Coming back to this. So we answered those 2 questions with our rounding, and we're going to fail to reject. So we do not reject this one of these. The population mean is definitely, again, it's not. Again, there's just no reason to believe it's not the population mean. Okay, so I'm going to go with D for the answer. Do not reject H naught. There is no reason to believe that 37 inches is not the population mean at a significance level of 0.05. Okay. And again, and another reason why we don't say this, that the population mean, is that you didn't prove that it is. We didn't prove anything other than we're just not rejecting it. Okay. I'm not proving that it's 37 inches. I'm just saying that there's no reason to not suspect that. Okay. We're not proving anything. And then part C, explain why the t values and p values for part A and B are different. Okay. So this is all about that sample size. In here, everything depends upon the sample size. Okay. Notice that the p-value in here for the second one was smaller than the p-value for the large one. Okay. So if we look at these real quick, I'll show you. Notice that we had a small sample size. Here were the values. Okay. Notice that over here, the values got even smaller. The t value got smaller. The p value got smaller. So as you raise that sample size, everything went down because the t value and p value depend upon those sample sizes. Okay. So when we look at this, a large n causes a smaller standard error, narrowing the sample distribution with less area in the tails, and shows a larger, well, obviously it's not a larger p-value. Okay. So again, a larger n causes a large standard error with more area under the tail. That's not true because that was less area under the tails. Okay. So a larger n causes a smaller standard error with less area in the tails. That's true. And a smaller p-value, because the smaller the area, the smaller the p-value. It's got to be C, because everything got smaller as we increased that size. And again, a larger n causes a large standard error. No, it doesn't cause a large standard error. Okay. It causes a smaller standard error. Okay. So as I was saying, C, because our standard error is not going to get larger. It's going to get smaller. All right. So a larger n causes a smaller error. In other words, a narrower sampling distribution. With less area in the tails. As shown by the smaller p-value. Okay. And there you go. The larger the sample size, the smaller everything else becomes, because a t distribution depends upon that sample size. All right. Last question, number 25, and we did it. We survived. Number 25 is coming from 9.5. And it is a 2-sample hypothesis test. So all we got to do is answer these questions and we're good to go. All right. So up here it says a random sample of male college basketball players and a random sample of male college soccer players who were independently obtained. Sorry. So were obtained independently and weighed. Okay. Sorry, I just read that weird. So we obtained some basketball players and soccer players, males, and we weighed them. The accompanying table shows the unstacked weights in pounds. The distribution of both sets of the populations are normal. Determine whether the difference in means is significant. Use a significance level of 0.5. All right, so it says let mu basketball be the population mean weight of a male college basketball players, and let mu soccer be the population weight in pounds of male soccer players. So the hypothesis test, because we want to see is the difference significant? So in other words, is not the same is what they're saying. Okay. So when we look at this information right here, when we're thinking about the null hypothesis and the alternative hypothesis, so mu of baseball, that was basketball. Nope, baseball players. Sorry, I might have said basketball. Minus the mu of soccer. Remember, this first blank should always be in equals. So hopefully you select the equal for that. And then because we want to know if there is significant difference, that means the ha should be the not equals, because there's nothing up there that states whether it's larger or smaller. We just say that they are significantly different. So that means not equals is the second blank. Okay. So we've got equals and not equals. And now we need to find this information. So we're going to have our calculator and we're going to put this information in and we're going to have it do its job. All right. So if I'm going to my calculator, I need to push stat and edit. and I'm going to put all the baseball players in L1. I'll put all the soccer players in L2. Watch how you input these. So 182, 193, 181. So this is like your kind of like longest problem in here. 176, 183. Sorry if you hear my daughter. I think she's pretending to be like a sorcerer or something like that. She's saying, feel my power. See, there she goes. She's so dramatic. 166, 202, 218. This is where you got to make sure that you're really, really careful, and we make sure that we get everybody in properly. 185, 163. And I'm going to know if I got everything in properly, because when I check all the data in the end, I should hopefully see the same numbers between my calculator here and StatCrunch, because I'm going to show you both. 78, 203, 188, 174, 174, 183, and there should be 30 of, I think 30 of these. Maybe it's 25. 190, 186, 172, 184, 181. Yeah, 25. 178. Okay. So now putting in my soccer players. 157, 183, 180, 176, 176, 180, 161, 172, 166, 174, 161, 181, 178. And then kind of going to lose sight of these. So 147, 157, 166, 149, 141, 162, 175, 173, 168, 184, 151, 154, and I ended on 25 there. So that's a good sign. Okay. So here, now we'll go to stat, tests, and this time you're doing a 2 sample t-test. So scroll down to 2 sample t-test. You're doing it from data, your list 1, list 2, that's correct. And you want to choose the not equals. So all this is good, and you leave the pooled alone. So all we got to do is come down to is calculate. Okay. And there's all of our information that we want. So we'll talk about this information here in just a second. Let's go to StatCrunch and get that information and make sure that we have everything that we need. So in StatCrunch, again, you'll go here. Oops, sorry, we're not doing that. Let's get rid of this information too. So here we got baseball, and over here we got soccer. Grab this piece of information, kind of slide it to the side there so I can start putting all my stuff in. Oh no. Oops. Let's do this. Here we go. Gonna slide this over. Crazy things are going on. Let's go back to this. All right, here we go. Now we got it. All right. So now that I got everything situated, 182, 193, 181, 176, 183, 198, 178, 166, 202, 218, 225, 185, 163, 178, 203, 188, 174, 174, 183, 190, 186, 172, 184, 181, 178, and 25. Good. And then 157. As long as I'm putting these in correctly, everything's going to work out perfectly in the end. 176, 176. Oops, did I got a slash in there? I did. 176. 180, 161, 172, 166, 174, 161, 181, 178, 147, 157, 166, 149, 141, 162, 175, almost getting there, 173, 168, 184, 151, and 154. Boom, there we go. All right. So now I can turn these back to large size. Maximize. Okay. So in here, stat, T-stat, to sample with data. Okay. So we select baseball, we select soccer, and 0 and not equals is what we want. Compute. So here's what we know. Let's make sure this matches what I know over here. So 4.912864, 4.912865, which is about right because 64, the 6 says, hey, 4 round up. So yeah, that's good. And this is a very small number, which over here, yep, that matches. If we look at some other things, degrees of freedom is 46.74, and checking this one, 46.7. Yeah, that matches. So we're pretty good. The mean is 85.64. Let's just double check this. If these match, then I'm pretty sure I entered everything right. So doesn't tell me what they are, but if I did stat or summary columns compute, so 85.64, 85.64, good. And let me just check the other one. This is just making sure that all my data is correct. So numbers are checking out, which is a good sign. Calculate or stats columns. Let's check soccer real quick. Compute. So the mean is 66.88. 66, yeah, good. So everything checks out. So that means I'm fairly confident that I put all the right numbers in both of these. So now we can answer the questions. So it says, what is the t-statistic? 2 variables. So t is equal to, I like to use StatCrunch. So I can get rid of these. I don't need those up here. StatCrunch, the t-stat is 4.91. Rather than 2 decimal places, which matches over here, 4.91. Okay, now let's talk about this piece right here. This is probably where the calculator is a little bit better. This actually gives us the p-value, which is 1.146639988 e to the negative 5. Okay, so let's talk about what that e to the negative 5 means. If you don't remember, e to the negative 5, this means that this is scientific notation, which means that this is really 1.146639988 times 10 to the negative 5. That means that this is a really, really small number, that we just need to move this decimal 5 places to the left, and that's the real p-value, which looks like this if we move the decimal 5 places to the left. Because the decimal's right here, 1, 2, 3, 4, 5. This is the real p-value. And if you round this to 3 decimals, you're just going to have 0.000. And they do want that in the blank, which is why you see on StatCrunch, it says this, 0.0001, less than that, because it's it's a really, really small number. Our p-value, as you saw, is definitely less than 0.0001. Okay, it's extremely small, but that's what they want in that blank, 0.000. Okay, make sure that you put that in there. All right, so with that being said, they told us our alpha is, I believe, a significance level of 0.05. So our question is, since alpha is 0.005, or 0.05, sorry, is 0.000 less than or equal to or greater than 0.05? And hopefully you chose the less than, which means we're going to reject the null hypothesis. Excuse me. Reject the null. So we're going to come back here. And in this blank, we're going to say reject. And then over here at the 0.05 significance level, there blank sufficient evidence. There is sufficient evidence to conclude that the difference in mean weights is significant. So you're going to select the word is. We have sufficient evidence. And that right there is the exam. That is what you need to be able to complete for us in this exam 3, which covers chapter 7, chapter 8, and chapter 9. You stay classy, statistics students.